Assalamu alaikum, ladies and gentlemen. You are welcome to the fourth program in the series of operating system programs. When I think of today's topic of discussion, I remember the quotation from the Future Shock of the Alvin Toffler, the celebrated American author, in which he says, all things from tiniest viruses to the greatest galaxies in reality are not things at all, but processes. And he keeps on saying that the different processes proceed at varying speeds. Time is the currency with which we can measure the speed of change. And in our previous discussion, we settled on a definition of processes, that processes are programs in execution which consist of its address space, also known as its core image, and the process table. And we also will be reminded that we also understood that process table contains information about the processes, about the files, and about the memory in the operating systems. Further, in our previous discussions, we discussed that a process can create the children and grandchildren. As such, it forms a hierarchy. We also learned in our previous sessions that process hierarchy cannot go very deep, 2 to 3 levels. We also learned that process hierarchy is short-lived. As early as the process gets completed, the hierarchy shortens, new process added, hierarchy deepens. And we also learned that the ownership of the processes cannot change. That moves us to our today's discussion about processes. We'll discuss the process model. We'll learn the concept of pseudo-parallelism, how processes are created and terminated, and the concept of process states. We'll also learn today about the inter-process communication. We'll look at the race conditions, the concept of mutual exclusion, the critical region concept, and what conditions should be held for a best solution in case of race conditions. Then we'll discuss some solution algorithms, which includes disabling interrupts, lock variables, strict alternation, and few others. And then we'll look up at some classical process synchronization problems. Ladies and gentlemen, now while we have settled on the definition of a process, and now we know that process is an activity of some kind, which has inputs as well as outputs, and the process converts input into output. You would certainly like to know how the processes are created and how the processes are terminated. I believe in our previous discussions, we have learned that whenever the system initializes, the number of processes, processes come into being. And whenever you log on the system, again, a process specific to your user ID gets created. And now, when you try to do something with the computer, download a file, print a file, look at the database, send an email, processes gets created. And similarly, when you complete a process, let's say you are printing a file, when it's printed, process terminates. Whenever download is complete, process terminated. These are the processes which terminate when they are complete, it terminates. As long as the process is doing something, the process is in function. Whenever the activity completes, process gets terminated. You would like to learn more about the difference between the process and the program. We'll like to learn that with the help of an example. Let's say a computer programmer promises with his daughter that he will bake a cake for her at her birthday. He has a recipe book. He also has a well-stuffed kitchen in which he has eggs, sugar, stuff like that. the computer programmer starts looking at the recipe book and starts baking the cake. In this example, recipe book is a program and computer programmer is the processor. And the process of baking cake, which converts the input into a cake, will be essentially a process. Okay, now while the computer programmer is baking a cake, while he is in the middle of that, his son keeps on rushing and shouting that he has been stung by a bee. Now computer programmer stops whatever he is doing in baking the cake, saves that information in his mind, and takes out the first aid kit, reads the instructions, and administers the first aid to his son. Now he has done, the two processes have taken place. One, he was baking a cake. Number two, he has administered the first aid. We see two distinct activities taking place, one after the other. Now you take an example of while you are at the computer, you are doing a number of processes. Let's say you are printing a file, you are downloading a file, you are looking at the database, and so on. Number of activities, and it seems that all these activities are taking place at the same time. That is not the case. The computer processor is handling one activity at a time. The processor is handling one activity at a time, although it seems that all the processes are taking place in parallel, which is not the case. And that concept is called pseudo-parallelism. Pseudo-parallelism. Now we move on to, with this discussion, we move on to the process model concept, and we'll like to learn that with the help of an example. Let's go to this example. We see here in the process model that program A, program B, program C, program D, all in the computer memory and being executed. This is the multi-programming example, that in the memory there are multiple programs. We extend the same concept since we said that processor is doing one activity at a time. We can say that downloading a file is a process, printing the file is a process, compiling the program is a process, downloading the looking at the database is a process, and all these processes, they are primarily sequential processes, which is clear in the diagram C. We say processor gives time to activity A. When activity A takes adequate share of the processor time, it goes to activity B, and then once the activity B has taken its share of the CPU time, then activity D, and again we come back to activity A, B, and C. We see that CPU is giving time to activity A, B, C, D, again to A, B, C, and D. It means the computer CPU or the processor is giving time to all these activities sequentially. Let's look at with another example, with another diagram. We see that the scheduler of the operating system giving time to process 0, process 1, 2, 3, n minus 2, n minus 1. It means the computer is giving time in sequence, not in parallel. Although the activities seem to be happening in parallel, it is not. From this, a logical question arises. You would say, when processor is serving only one process at a time, what other processes are doing? Essentially, they go in different states, and they are either running, it means they are using the CPU time, or they are ready, means they are waiting for their turn to come to be served by CPU, or they are blocked. That means that they are waiting an input or some external variable to intervene to go from the blocked state to the ready state. Once again, the processes could be in either of these three states. Number one, either the process is running, the process is actually using the CPU time, or the process is ready, that means it is runnable temporarily on hold because CPU is serving some other process, or it is blocked, unable to run until some external event happens, for example, input from some external process. Let's understand that. Let's explain that with the help of another diagram. We see process running, actually taking the CPU time. From the running state, either the process could go into the block state, which is the condition 1, or the process could go into the ready state because the CPU scheduler decides that the running process has taken adequate time of its share and now some other process should be served. Or if the process is ready, then scheduler picks this process and from the ready state it takes to the running state. Or when this happens, now come to the block process, which is waiting for some external input. That input becomes available, the process from the blocked state, it goes to a ready state. With this, we move on to our next concept, which is about the inter-process communication. In most of the operating systems, very often the processes working together, they share common storage. That storage may be in the shape of a shared file, in the shape of a shared variable, or in the shape of a shared memory. When the two processes or multiple processes share some space, a number of conditions, number of things happen. Let's take an example of print spooler. For the processes to access that spooler directory and see if there is an empty space in the spooler directory, if they can print, or the daemon comes and wants to see if there is something to be printed, it is essentially handled with two shared variables. For example, the out variable points to the file's next file to be printed, and in variable points to next available slot in the spooler directory. Let's try to understand that with the help of a diagram. We see here the spooler directory. We see number of slots in which 4, 5, 6 are the files or file names to be printed, whereas slot 7 is empty. We see the daemon comes and see out number 4 is ready for the printer. So the daemon comes and takes this ABC file for the printout. Now two processes, process A and process B comes and they want to print a file. Process A wants to print a file, process B wants to print a file, and they all reach the slot 7 at the same time. Now process A reads that slot 7 is empty, and before the process A writes the file name in slot 7, CPU decides that process A has taken enough of its time. It stops there. Now process B comes and finds that slot 7 is empty, writes the file name to be printed. Since this process A has already read about that slot 7 was empty, process A overwrites the file name which process B has written already in slot 7. This condition where process A and process B, they come and try to use the shared variable is called a race condition. What will happen here is the process A will get its output, but process B will not, because process B got overwritten by process A. Okay, let's try to understand and discuss this race condition in a little greater details. When two or more processes are reading or writing some shared data in the shape of shared storage, shared memory, shared file, or a shared variable, the final results depend on who runs precisely when, and we call it the race conditions. Once again, when two or more processes, they try to access a shared variable in the shape of shared file, shared storage, or a shared data, and the final result depends who reaches to that variable first, or who in certain point of time is where in that process, the final result will depend on that. And multiple processes trying to access the same shared variable is called race conditions. And how we can essentially overcome that, that is a question of fundamental importance in the operating system arena. Okay. We can handle that process with mutual exclusion. And what is mutual exclusion? When two or more processors are trying to access a shared variable, trying to use a shared variable, the other processes are excluded from that. When multiple processes are trying to reach a shared variable, and the process who gets first starts doing it, and the other processes are excluded from doing the same thing. And we invoke another concept here, which is called the critical region. What is the critical region? Whenever a process tries to access to a shared variable, whenever a process tries to access a shared variable, in that part of the program is called its critical region. And how we can achieve mutual exclusion is that if one program is in its critical region, all other programs are excluded. They should not come into their critical region. I'll read the definition of critical region once again. That part of the program where the shared memory is accessed, it called the critical region of that program. If we are able to manage that no two processes reach in their critical region at the same time, race conditions could be avoided. Let's try to understand this critical region concept with the help of an example. We see here process A and process B. We see that process A enters its critical region, and while process A is in its critical region, process B tries to enter in its critical region and it's blocked. Process B is blocked to enter in its critical region. Now, once the process A leaves its critical region, now process B can enter into its critical region. And then process B completes its algorithm in the critical region, and process B again leaves the critical region. Now another process could come and enter in its critical region. As long as any process A or process B is in its critical region, other processes are excluded, should be excluded to avoid the race conditions. There are 4 conditions that should be met for an ideal synchronization problem amongst the processes. Condition 1 is that no two processes should be allowed to enter in their critical region at the same time. Second, we should not make any assumptions about the number of processes as well as speed of the CPUs. We should not make any assumption about that. Number 3 is no processes running outside of its critical region may block another process, and the last is no process have to wait forever to enter to its critical region. We have to design a solution. We have to design an algorithm which best suits the synchronization amongst the processes. We'll briefly discuss the elementary algorithms in process synchronization. Okay, let's look at the algorithms which are available. For example, we have we can achieve mutual exclusion by busy waiting, and the schemas we have is disabling interrupt, use of the lock variable, strict alternation, Peterson solution, test and set lock, while we have some other algorithms like semaphores, monitors, event counters, message passing, sleep and wake up system calls. Let's look at the first three one by one, disabling interrupts first. In disabling interrupt, which allows a process to disable interrupts before it enters its critical section and then enables interrupt after it leaves its critical section. And in this, CPU will be unable to switch processes once the interrupts are disabled. And then it guarantees that the process can use the shared variable without another process accessing it. This algorithm is useful and handy for the system processes. Only the operating system should be able to disable interrupts and then enable interrupts. You cannot leave the control or the option to the user programs to disable interrupts or enable interrupts, because that way you can really kill your system. We have another concept of using the lock variable. For example, the process which tries to enter into its critical region sets a variable or locks a variable, let's say 1, when the process is in its critical section, and reset to 0 when the process exits its critical section. Once again, when the process enters in its critical section, it sets the lock to certain number or certain value. When that process leaves its critical section, it resets the lock and another process could come and enter in its critical section. But this algorithm may be useful to some extent. It has the same flaws which we saw in the spooler directory example. Some process is in the middle of using the CPU time, scheduler decides that time is over, another process comes and overwrites. As such, the algorithm is flawed, except it passes the responsibility from the shared variable to lock variable. Computer programmers have worked on another algorithm that is called the strict alternation. We see this process A. When the process sees that the turn is set to 0, it is assumed that when the turn is set to 0, process A can use and enter into its critical region. Okay. When the process A completes the critical section, it sets the turn to 1. As such, some other process could come and enter in its critical section. Now the process B, it sees that turn is set to 1, process B can enter in its critical section. When process B leaves the critical section, it sets the turn to 0, and so on. Do you see a problem here? Yes, there is a problem. The difficulties or the problem in strict alternation algorithm, process A runs, enters its critical section and exits, setting turn to 1. Process A is now in its non-critical section. Assume that this non-critical procedure takes a long time. Process B, which is much faster process, now runs, and once it has left its critical section, turn is set to 0. Process B executes its non-critical section very quickly and return to the top of the procedure. The situation is now that process A is in its non-critical section and process B is waiting for turn to be set to 1. In fact, there is no reason why process B cannot enter in its critical region, because the process A is not in its critical region. The computer scientists have also worked on a number of algorithms. For example, Peterson solution and test and set lock algorithms. These two algorithms, Peterson solution and test and set lock, they do provide solution to the race condition, but they cannot overcome the busy waiting phenomena. Once a process comes and see the variable is being used, some other process is in its critical region, the other process will come and again and again and again, will see until it will find that that process has left its critical section. It is the wastage of precious computing resources. We'll not go, as I mentioned earlier, in the detailed analysis of these algorithms. We will cover these algorithms and some other in some advanced operating system courses. To recap our discussion for today, what we covered was, we discussed the process model, we discussed the race conditions and the situations in which race conditions occur, and then we looked at the algorithms with which we can overcome the race conditions. That wraps up our discussion for today. In the next session, we plan to discuss the process scheduling, how the process scheduler in the operating system schedule the process, and at the same time we would like to have some practical exercises. We'll run some practical algorithms or practical commands to see how the processes can be managed. With this, we complete our today's program and we conclude our today's discussion. Allah Hafiz.